All right, let's see here. So we got parametric equations in calculus. So we've talked about graphing parametric equations, and we've looked at how there's two different functions controlled by a third parameter t, one function for x and one function for y. So the first thing we need to be able to do is figure out an equation for the derivative of this overall function, but in terms of t. So we want this thing to be in terms of t. That way, if I said, hey, what's the slope at time pi, you could just immediately plug in pi. You wouldn't need to go convert to xy and then plug it in. So the first thing we're going to do, we're going to say y equals capital F of x. And what we're looking for is f prime of x. So with a little substitution, we're going to go ahead and replace y with g of t. And then at the same time, we're going to replace x with f of t. So y is going to be g of t, and x is going to be f of t. That way now we're in terms of t. Next we're going to take a derivative of both sides. So g prime of t equals f prime of f of t. And then we got to chain rule this, so it's times f prime of t. Okay, now we're going to back substitute again, and we're going to replace f prime of t back with x. And so now on the right, I'm going to have f prime of x, which, if we remember, that was our goal up here. We wanted f prime of x. Divide both sides by f prime of t, and it's going to equal g prime of t over f prime of t. And this should make sense. What we're getting is the slope is g prime of t, which means rate of change of y, over f prime of t, which is rate of change of f. So the slope is change in y over change in x, which is what we've been saying for years. Delta y over delta x, y2 minus y1 over x2 minus x1, change in y, change in x, slope. Okay, so that works out very nicely for us. So here we have the parametric form of the derivative. Formally, dy dx equals g prime of t over f prime of t. That's generally not how we write it. You see more the dy dt over dx dt. If you were to stack and eliminate dy dt over dx dt, so keep, change, flip, whatever you call that. So dy dt times dt dx. What we notice here is the dt's go away, eliminate to 1. So what I'm left with is dy dx, which is exactly what we claimed over here. Okay, very nice. So how do we use this? What are the types of questions they're going to ask? First thing they're going to ask us to do is generally find a tangent line. So my goal is tangent line. So it's like it's August again. We think back, what are the two things I need for tangent lines? I need a point and I need a slope. So they gave us a function, x equals secant t, y equals tangent t, on an interval for time. Find the equation of the tangent line at pi over 4. So here's the graph of this function. At the moment, all we have is time equals pi over 4. So if I just said, hey, point to where it's pi over 4, we don't know that. There's not a t-axis on this coordinate plane. So the first thing we have to do is figure out the actual point at time equals pi over 4. So we just take my x equation, which is secant of pi over 4, and we take my y equation, which is tangent of pi over 4. All right, you can't let your trig hold you back here. So the secant of pi over 4 is 2 over root 2, and the tangent of pi over 4 is 1. So we have my point, which is 2 over square root of 2, comma 1. So for a tangent line, we need a point and we need a slope. So there's the point in blue. So now we see where that tangent line needs to be tangent. So we can kind of imagine what it should look like at this moment. But the next thing I need to do is calculate the slope at that point in order to find my tangent line. So dy dx is dy dt over dx dt, what we just discovered up top. So dy dt, that's the derivative of tangent t. Okay, so that's secant squared t. And then dx dt is the derivative of secant, which is secant t tangent t. All right, that is a functional derivative. You could totally plug in pi over 4 right there. might be a little harder. You should be able to reduce this. So a secant will cross out. So this becomes secant t over tangent t. You could also plug it in there. That still reduces further though, because that's 1 over cosine t over sine t over cosine t. And then if you outside, inside, keep, change, flip, reduce, whatever you want to call it, that's 1 over sine t, which equals cosecant t. So now I'm going to plug in, so such that time equals pi over 4. And my slope winds up being, so that's sine of pi over 4 flipped, so it's 2 over the square root of 2. So there's my slope at this point. So now I have everything I need for a tangent line. So my tangent line being y minus y1 equals m, and then x minus x1. Tangent line. If we go graph that to make sure that it's working, boom, there it is in green, perfectly tangent to our point on the red curve. All right, so the next question is a little bit of a twist on this. So looking at it, they've given us a parametric function. It's defined by x and y, controlled by a third parameter t. Find the equation of the tangent line at this point. So they seem to be generous in the fact that they've already given me the point. The problem is, what that means is you have to work backwards and find the time. Because when I go to find the slope, so dy dx, and you should always write is dy dt over dx dt. It's just good practice, helps you remember it. Okay, so dy dt on top, so 2 minus pi. So that gives me pi sine t over 2 minus pi cosine t. If you need to stop and make sure you check and understand those derivatives, do that. All right, so the problem is I can't plug in 0, 2 to that because 0 is an x value and 2 is a y value, and the only variable in that derivative is t. So what I have to do is I have to work backwards. So I have to say, well, x is 2t minus pi sine t, and y equals 2 minus pi cosine t. So I need that x needs to be 0 and y needs to be 2. According to my ordered pair, 0, 2. So what I need is the t value that's going to simultaneously make both of these true. There could be multiple t's that make different ones true, but I need the one that's going to make them both true. Okay, so I'm going to have to solve one. One will generally be easier to solve than the other. On the right, if you subtract 2 and then divide by negative pi, you get cosine of t equals 0. Okay, key here becomes this thing, my domain restriction. So time, the time constraint they gave us was negative pi to pi. So when we're thinking about where is cosine 0, my answers, there's 2 of them. It's negative pi over 2 and pi over 2. So there's 2 different times on the right. So now I got to go over to the left. There technically are more outside of this domain, 3 pi over 2, 5 pi over 2, whatever. Like there's lots and lots and lots of them, but they don't fit on the restriction. So I'm not done there. I have to verify that that's going to make the other equation true as well. So we got 0 equals 2 times pi over 2 minus pi, and then sine of pi over 2 is 1. So we get 0 equals pi minus pi, which works. So pi over 2 totally works. And then the other one, I want to check them both. So 2 times negative pi over 2 minus pi sine of negative pi over 2. Sine of negative pi over 2 is negative 1. So this one works as well. So those are my 2 times here. All right, so I need the slopes at those times. So dy dx such that t equals pi over 2. So that's going to give me pi, and then sine of pi over 2 is just 1 over 2 minus pi, and then cosine of pi over 2 is 0. So that looks like pi over 2. So my first tangent line, so I'm using the point 0, 2, and I got a slope pi over 2. So I got y minus 2 equals pi over 2. times x minus 0. So there's my first tangent line. And then I need to recalculate the slope at time negative pi over 2. So that looks like pi, and then sine of negative pi over 2 is going to be negative 1 over 2 minus 0 again. So it's just negative pi over 2. So my second tangent line is y minus 2 equals negative pi over 2, x minus 0. So there's two different equations. Find the equations of a tangent line at this point. And if I go look at the graph, I can see this. So here's this function, and we're looping around to be tangent at 0, 2, so that black dot. So what we see is there is the increasing tangent line here in red, and then also there's the decreasing tangent line there in blue. So we do have both of those things. That's a little tricky. To catch both of those is a little tough. All right, so that's tangent lines. Those are the two different ways they could present and ask those questions. One is giving you the time and asking you to find the point. The second would be giving you the point and you having to work backwards to find the time. So make sure you can handle both of those. Example 4 is going to cover the next things that they like to ask us to do. So where it has horizontal tangents, vertical tangents, x and y intercepts. So we need to know the quick process to do these things. So horizontal tangent. We got to think about, what does that mean? If a function is horizontally tangent, it looks like that curve. It's flat. So what does it not have? It's not going up and it's not going down. We can define up and down by dy dt specifically. So dy dt is your change in y over time. Well, if I'm horizontally flat, I don't have any change in y. So horizontally tangent means dy dt equals 0. Vertically tangent, so straight up and down, means you shouldn't have any wiggle, if you will, left and right. So my x values aren't changing. The x value is consistent. A tangent line that's vertical, or a vertical line, is described as x equals 4. So x is always 4. It's not changing. So there's no change in x. So dx dt, my changing in x over time, needs to be 0. All right, so this totally also makes sense in the grand scheme of dy dx. So dy dx is dy dt over dx dt. So if we want something to be horizontal, we know we want this dy dx to equal 0. How do I make dy dx equal 0? I make the numerator 0, which is dy dt equals 0. So it's quicker. So you're not wrong to say, how do I make something horizontal? I make dy dx 0. That's true. But it's more efficient to say I want dy dt to equal 0. So that's less steps. How do I make something vertical? You're not wrong to say that I want dy dx to be undefined. But how do I make dy dx undefined? I make the denominator undefined. And how do I make the I make the denominator 0. How do I accomplish that? I make dx dt 0. So those are my shorter methods for this problem. So let's go and attack those two. So determine where it has horizontal and vertical tangents. So I want dy dt to be 0. So the first thing is dy dt. I got to find it. So dy dt looks like it's going to be 3t squared minus 3. So I need to set that equal to 0. So t squared equals 1. So t equals plus or minus 1. All right, now that doesn't answer the question. It says where it's horizontally tangent, t equals 1, and minus 1 is when. So I need to now plug in t equals 1 to my x and my y equations. So I get ordered pairs. I'm just going to go ahead and tell you they're 1 comma negative 2. Hopefully you can plug in things. And you're going to get 1 comma positive 2. So those are my horizontal tangents. Need to do the same thing for a vertically tangent. So I need to set dx dt equal to 0. So dx dt is 2t. So t equals 0. That's again a when. So t equals 0 gives me an ordered pair of 0 comma 0. I'm just plugging in for x and plugging in for y. Boom. So that's where am I horizontally tangent, where am I vertically tangent. The next two things it asks are about x and y intercepts. X intercepts, so hopefully you remember this from middle school. If I'm on the x-axis, my y value is none. So to find my x-intercept, I set y equal to 0. So x-intercept you set y equal to 0, which means t cubed minus 3t equals 0. We're in calculus 2 now, so that can't be your end. You can't get to there and just be derailed. Like, you got to be able to factor out a t and say t squared minus 3 equals 0. Boom. T equals 0, t equals plus or minus the square root of 3. So that gives me 3 values. We already know the ordered pair for 0. Plus or minus the square root of 3 is going to give me 3, 0 and 3, 0 again. So those are my x-intercepts. Last thing is my y-intercepts. Likewise, if I'm on the y-axis, my x value has to be 0. So how do I find the y-intercept? You set x equal to 0. So I got t squared equals 0. Once again, t equals 0 gives me an ordered pair of 0, 0. So if I were to go sketch this now, I've got a lot of different characteristics that I've defined. So if I were to try to draw a sketch of this parametric curve, getting ahead of myself, go plot things in order of the time components. So what we have is at time equals negative square root of 3. We're sitting here at 3, 0. And then, so I'll label that negative square root of 3. And then at time negative 1, that's when I was horizontal over here at 1, 2. And then I hit the origin at time 0. And then at time positive 1, I was down low. Negative 1, time 0, time positive 1. And then at time square root of 3, I'm back here. Okay, so I seem to be moving in this direction. Now, to think about the end behavior, like what's going to go on at the edges, think about the limits. So if you go back to your parametric form, x and y, so at time infinity, the limit of x at infinity is infinity, and the limit of y at infinity is infinity. So as the time increases forever, it's going to be shooting off to plus infinity, comma, plus infinity. And then where did it come from? So I'm moving around this parametric curve in this direction and beyond. So where did it come from? Because we need to know, there are a few options, like does it come from here? Did it come from up there? Did it come from down there? Did I come from back there? So there are a few kind of what ifs. So I need to know my time at my limits at negative infinity. So the x value at negative infinity is still positive infinity, negative infinity squared, positive infinity, and the y value is now negative infinity. So it does come up from positive infinity, comma, negative infinity, which is down this direction. So the curve came from down here. So there's my little sketch of this thing. And if we could go and we want a more perfect sketch, there it is on Desmos. All right, so those are the things from day 1 about parametrics that you need to be able to do. Write the equation, find the slope, but write the equation in the tangent line given a time and then given a point and working backwards to find time. Then you also need to be able to find horizontal and vertical tangents and x and y intercepts. And that's all.